for now. Yeah. Okay. Anyway, so the next principle is Le Chatelier's principle. I think that's a French name. Anyway, so first let's look at the equilibrium. So equilibrium is reached when a reaction is at a point where the composition of reactant from product is just balanced by the reverse reaction of the products combined to form the reactant. So basically, equilibrium describes a reverse chemical reaction. And under the situation when the A and B, the rate when A and B are consumed equals to the rate when A and B they are produced. So they are at a dynamic and steady state. So in this case, we have the Le Chatelier's principle, which says like this: if a stress is applied to a system in a dynamic equilibrium, the system will adjust to release that stress. So, but we have too much homework when we do this, but please do not do this in this class. But in chemistry, the explanations are pretty similar. So for a chemical reaction at equilibrium, a reaction will adjust itself in such way to relieve any force or stress that distributes, that disturbs the equilibrium. So basically, we want to just release that stress. And to be more specific, we can look at two examples. So for this one, we have this reverse equation, which A plus B will generate C and D. So what happens when we add A to the solution or to this system? We can see that if we add A, the concentration, like the A will increase. And because the A increase and the system want to release their stress, the reaction will go in from left to the right. So it goes to this direction, we will have more D and more C. And we will have less B because the B will consume. So in this case, if we add A to this system, A will increase, B will decrease, C will increase, and D will increase because this reaction goes to this direction. And another question is, what happens if we remove C from the solution? So in this case, C is removed. So the concentration of C is decreased, and this system wants to compensate the loss of C. So again, it will also go to this direction because it wants to generate more C. So in this case, when we know it goes to this direction, we know that D will increase, and B will decrease, A will decrease. So it will be something like this. Yes.
Can you give an example of the direction going another way?
Okay. Yes. Like we have A plus B contains 3 and D. So yes, we can also frame the question like, how can we let the reaction goes to this direction? So if we want to go to this direction, we want to put more stress. I would say put more C or D, because if we increase C, it will release this stress. So it wants to decrease the concentration of C. So it will go to this direction. And in this case, D will decrease and A and B will increase. Right. So when we are looking at this question, first, we can determine what's the direction of the reaction will be. And after determining the direction, we can know the increase or decrease of each component. So for this one, have more questions? No. And actually, for this case, we have some practice, like for some of the industrial manufacture, we only want B and we want to have more D. In this case, we can just remove another product. So for the final results, we will have a relative high concentration of D. Okay, the next, so more about equilibrium. So for this one, this is a simple form, but to be more specific, we know that for the chemical reaction, they have the coefficient before each one. So a more general form could be this one. And so for this one, we can have a parameter to describe the equilibrium, which is equilibrium constant, KEQ. So this is just to describe when it is at equilibrium, which means the concentration of A, B, C, D, they will not change. So in this case, this KEQ equals to this reaction. So we can see this is the concentration of C, and the order is its coefficient. And similarly, we have the concentration of one component, and we have its coefficients as its order. So, so basically, that is the product divided by the reactant. And we also have some coefficients in the front of this. And here shows an example. If we have a chemical reaction of this one, this is relatively simple. So this is N2O4 and this is NO2. And N2O4 is transparent and NO2 is brown, and it is toxic. So for this reaction, we can see that KEQ refers to the product. The product is NO2, so we put NO2 here. And the coefficient is 2, so the order is 2 here. And divided by the concentration of the reactant, and the coefficient is 1, so it equals to this one. And for the equilibrium constant of a given reaction, we can usually find it on Wikipedia or on the internet. And so for this one, do you guys have any questions? No. And the next one is about calculation, like the stoichiometry. Anyway, so basically, we are having some chemical reactions, and we usually care about the mass instead of the moles. So if we want to calculate the mass of the reactant, if we want to calculate the mass of the product, and we usually know the mass of a reactant, we cannot directly to do this calculation, but we need to use the moles as the bridge to do the calculation. And here is an example. Let's just take a look at it. So the question is, how many grams of CO2 are obtained by the complete combustion of this gram of butane? And so the butane is, like, we usually use the butane as an energy fuel. And so we can just put this into the stove, and then we can make some foods like hot pot. Okay, and so in this case, first, we can write the chemical reaction. So the butane is oxidized by oxygen, and it will generate CO2 and water. So this first step, we need to know its chemical reaction. Second, we need to balance this chemical reaction based on the mass conservative principles. In this case, we can calculate the coefficient of each chemical. And then we want to calculate the number of moles of the reactant or the butane. And based on the calculation, we can see that the molecular weight of butane, I think this could also be expressed, that is gram per mole. And so we use this mass divided by the molecular weight. We can obtain the number of moles of the butane. And in this case, we can use the mole ratio to determine the amount of CO2 that is produced. We can see that this is 1, and the coefficient is 4, which means the moles of CO2 is 4 times of the amount of butane. So we use this times 4 So we use this coefficient here to multiply the moles of butane, and then we can get the moles of CO2. And finally, we use the moles of CO2 times its molecular weight to obtain the mass of CO2. So basically, we use the mass to calculate the moles, and the moles to calculate another mole. And then we use the moles to calculate the mass that we want. And so do you guys have any questions about this one? You guys may take a look at this and calculate it by yourself. The next one is limiting reagents. So because of the time, I'm not going to read these two, and they are relatively not that important in this class, but I want to emphasize the pH. pH is a measure of how acid and base water is, and the range goes from 0 to 14. And usually the 7 refers to the neutral. And the pH is defined as the, so here is the concentration of H plus in the water. And then we take the log 10 of this concentration. And then we add a minus to this one. And this is pH. So basically the P, this transformation refers to the minus log 10 of something. And the last one, I believe this should be the last one, is acid dissociation constant. I think you guys may also learn it in 310. So if we remember, if we can remember that we have pKa and Ka, no matter what is that, but these two parameters can use to describe the weakness or strongness of an acid. And the smaller pKa refers to stronger acid, and the larger pK or Ka refers to stronger acids. So basically, we can use these two parameters to compare the strength of an acid. And here just show the definition, like the mathematical definition of pKa. So for a weak acid, it has this dissociation equation. And we also learned the expression of equilibrium constant, which can be expressed as this one. So we can just plug this concentration in this equation, and we can have this result because the coefficients are all 1. So we can define this as Ka, which is acid dissociation constant. And again, we can apply P, this transformation, to this Ka, and then we can have pKa equals to this one. So Ka and pKa, they are just one thing, but has different scales or different transformations. And again, we can find like some tables that describe different acids, and usually the pKa or Ka, they will be given, and we can use this to compare the strengths of different acids. And the last thing I want to say that we can see that we know the definition of pKa and we also know the definition of pH. So basically the pH is a function of H plus, and in pKa, we also have H plus here. So we can do some mathematical transformation. We can find the relation between pH and pKa. So what this tells us, just a little bit. So basically, it tells us two things. First, in practice, it is very easy to measure the concentration of the solution by a pH meter. So usually the pH is known, and the pKa can be found based on the tables. So in this case, we can use this relation to calculate the ratio between acid form between its dissociated form and undissociated form. So we can easily know the ratio between them. On the other hand, we can also say that when this term equals to 0, if this term equals to 0, it means HA equals to A minus. So in this case, this term equals to 0. At this point, pH equals to pKa. So when pH equals to pKa, we know that their concentrations are equal. Or on the other hand, as long as their concentrations are equal, the pH that we measured reflects pKa. And I guess I will talk about this in the next lecture. And that's it for today. So for the ending notes, you guys may start doing CRISP-1, and for CRISP-1, you may use like this file. And this file is under the syllabus. So you guys may take a look at this file first before taking CRISP-1 or CRISP-0. And that's it.
Do you ever post these like slides on Alex?
Yes, I will post it.
Okay.
Usually in the afternoon. Yeah, you can check it in the evening. Yeah. Mhm.
Are those strictly individual or can we work with people as long as we submit our own work at the end?
You mean assignment, which
Like assignment one, can I like tell us to work with some people in class to help each other out? Is that?
so assignment 1 is individual, and you can see the instruction. I already posted the solution, so it's just a practice. Yeah, so that is for the individual. Oops.
Quiz 1 is on chemistry stuff though.
Yes.
Okay.
Yeah, so this is.
I assume that will be common practice though.
Yes. So you just need to send me the self-evaluation. Like I'm good with this question, I'm not good at this that
So it's like
question.
a
So-
fresh in my head.
Oh, so you mean for every assignment?
No, only assignment.
Oh, it is only.
A little bit.
Yeah.
Yes, I think-
Mhm.
Like, I
Well,
remember
thanks so much.
one, just
No
like,
problem.
no problem, like, do it, right? Like I need to go. Right.
Thank you.